key ideas on the importance density, especially since I lost those slides, or lost the recording of the lecture that I gave about that. So last time, this was all just review. Let me move aside a little bit. Can you see okay, Eric? Okay. So last time we talked a little bit about previously the example that we've been using, and the example I think all of you have still used so far in your homework for the importance density is just using the prior. And when you do that, there's this cancellation that occurs, and your weight update essentially becomes proportional to the likelihood function. So we've been doing that. This set of slides was calling into question why did we do that? And we talked about sort of a boneheaded thing you could do where you just completely ignore both your state dynamics as well as your measurement model and let your trajectories go without any consideration of either one. And you can do this, but then you really need Reed's computers and code optimization skills to have a hope, to have enough particles to have a hope that will generate something reasonable. And then this was a key slide from last time where we talked about an idea of trying to minimize the variance of the weights. We know the weights have to be between 0 and 1. If we minimize the variance, then that should mean all the weights are constant. But then, and you'll find this in a lot of the articles that are trying to teach about particle filters, this idea of a so-called optimal importance density, and they use this criterion. And last time I called into question, I said, I don't believe this, I don't like this, because the expectation is being taken with respect to the importance density conditioned on the past. This past is not on the left side, it's given that you know what the past is, and the weights depend on that. And so I think the criterion, the way they defined this expectation, I don't think makes a lot of sense. It reduces the variance, but it doesn't result in your weights being constant. And we already knew what the optimal importance density was. So the idea of finding an optimal, where this is your definition of optimality, I still don't think that's the right idea. Nonetheless, it helps. I mean, it's not a terrible idea to minimize this variance. It's just not as good as we would hope, where we're doing it over the entire trajectory and not just the way that we generate the state at time in, given the past things that we've generated. So we went through, and I didn't go through math last year, but at day, what we end up with is that the solution that minimizes the variance and in fact makes it equal to 0 as defined, given its limitations, is simply the probability of the state conditioned on what the state is at time n minus 1, as well as the measurement at time n. And this measurement at time n narrows the distribution. It gives you additional information about the state. And so when you take into account this measurement, it more accurately, one way of thinking about it is it more accurately guides this particle into a transition that is consistent with the measurement that you took. And so it makes sense from that standpoint. And then we went through and said, okay, well, if we're going to use that as our importance density, then if you go through and do the math, what's the weight update equation? And we went through more math, and what we ended up with is a very simple weight update, at least simple to write an expression for, where the weight is equal to something that looks kind of like the likelihood, but isn't, because it's the measurement at time n conditioned on what the state was one time sample back. That's different than what the state is currently, which is what the likelihood function is. So it looks similar, but this n minus 1 is different and not something that you can easily get from your model. So we end up with this as a weight update equation, and this is the so-called optimal importance density, and I continue to question whether that's really what you want. We already knew this is what we really wanted, and this is just what we got by using that definition of optimal. And then we saw this doesn't work. We can't draw samples from this importance density, so it seems like it's not any good. And then we said we also don't know how to evaluate this that we need for the weight update equation. This function is strange. And after just a little bit of math, we see that that we can relate this to the likelihood function and to the prior, but they're related by an integral. And evaluating integrals is part of what we're trying to avoid, especially in high dimensions. So One of the ideas that I started to propose last time is the idea of using a local linearization, which is how, prior to particle filters, is really how people took the linear common filter recursions that are designed for linear state space models and generalized them to make them work with nonlinear filters. So a lot of what we're seeing here should resonate with what you hear later in the term when we talk about those techniques, because it's a similar idea. It's a common theme. And then I hesitated because I had it wrong, but I said, consider this model, and even though this model is much more limited than what a lot of you are working with, almost all of you have been working with additive noise, and so the constraint of additive noise is not a big deal. And then we've got this linear term here, where y then is a matrix times what the state is. So we've got this linear observation equation. What most of you have been working with is actually a nonlinear measurement equation and actually a linear state update equation. So it's exactly the opposite. But it's under this condition that we can actually go through and solve for the things we need to use that optimal, so-called optimal importance density. And so this is worth going through, and I'll show you how to apply this to a nonlinear measurement equation in a minute. So there's a lot of usual assumptions here. Process model is nonlinear with additive noise, measure linear. And then these equations are right. And it turns out the equations I had on the slide last time were also correct. You'll see these are different equations, but they're both correct. There's multiple solutions that if you go through a lot of math, you can show that they're the same, and it takes a while to get there, but I checked it out, and it turned out to be right. So let me take a minute to go through this. I won't have time for the punchline, but I also want to point out some of these things because you're going to be seeing these again. A lot of these quantities here are used in the Kalman filter, the incentive Kalman filter, and a lot of the things we're going to be talking about later on. So this is a measure of the covariance of our predicted measurement. So if we take into account essentially all the past measurements and use our estimate of the state at time n-1 to estimate y, we can only estimate it so accurately. There's some error there. And this is essentially the covariance of that error, the difference between yn and the predicted measurement based on the estimate of the state, the previous state, and the past measurements. So this is an error covariance of the predicted measurement. This is a gain that is going to turn out to be the same as a Kalman filter gain that we'll encounter later in the term. So this Kn is a gain. You'll be seeing that lots. This is the covariance of how accurately we can estimate the state. So this is the state error covariance. So we've got an estimate of the state at time n that takes all the measurements into account up to time n. And this is essentially a measure of how accurately we can estimate the state. So it's the difference between x hat of n and what the state really is. The covariance of that difference is what this matrix represents. And then this is y hat of n and x hat of n.
So that covariance of the state estimation, is that an identity matrix minus k sub n, or is that 1 minus?
This is the identity matrix. Yeah, thanks for that question. So I'm not bringing you through the math. We've got lots of references for those. I'm trying to focus on the main ideas, but the thing that I want to point out is, given this information, we now, from this model, can show that the thing we needed, this probability that we want to draw samples from, turns out to have a normal distribution. And a normal distribution with a mean that we can calculate from those recursions, and a covariance that we can also calculate. And so we can use the same random number generator to draw samples from this distribution. And then this, likewise, turns out to be something we know. We needed this for the weight update equation. And in this particular case, we can get it. It also turns out to be a normal distribution, given the examples that we have, with this is the covariance and this is the mean. So, voila, in this case. And there's other ways of doing this. In most cases, you can't solve for the optimal importance density. A lot of the approaches that you can use end up being computationally intensive and start to miss on some of the rigor due to the approximations. But one uses a linear approach directly. In the interest of time, I'm going to slide and move on to this. This is the nonlinear case, and this represents what a lot of you have been working with. We've got additive noise, we've got a nonlinear measurement equation, and possibly a nonlinear process model. And in this case, the approximation is the familiar Taylor series approximation, where we approximate y of n at xn equal to its predicted value. So if we know what the state is at time x minus 1, we say, well, take your best guess of what it's going to be. Then if we substitute in x of n minus 1 here, we can't predict this noise because it's IID. So our best estimate is this. So this is the point that we linearize around. And then this is just the standard multidimensional or vectorized Taylor series approximation, but nonetheless, it's still a Taylor series approximation. And this ends up being very similar to the linear case, where this Jacobian is Hn, that observation mean. And so, after you're done, you end up with this algorithm for handling the nonlinear case, where this Hn is the Jacobian evaluated for each of the particles, the previous time step. You evaluate it at xn equal to that once you calculate the Jacobian, and then you put that through the equations, and you draw your particles accordingly, you update your weights as usual, normalize them if you need to, but it's essentially going through and using this linear approximation. And I went through and did this for the car tracking example to see how it affected performance. I didn't use 100,000 particles. And, it took a bit of math that, goes back to freshman year of college, to go through and remember maybe some of these identities and how to calculate these derivatives analytically. But in this case, when all is said and done, I was able to figure it out. It's a single dimensional example, so I was really just trying to figure out what it was in this case. And I figured it out, and that's what it was. Just as a precursor, in using the extended Kalman filter, you have to do the same thing if you're applying it to nonlinear problems. And there's this linearization based on taking the equivalent of a derivative, but it's a Jacobian in this case. And for large problems that people are applying the extended Kalman filter, this turns out to be the biggest problem, is going through and figuring out what that Jacobian is. People have spent weeks, months, going through and calculating the Jacobians and trying to make sure that they've got it right. Now we've got solvers now, we've got Mathematica and the symbolic toolbox that can make a lot of this easier. But historically, this has been where a lot of the errors have occurred, and it takes a lot of time to calculate these Jacobians. The incentive Kalman filter bypasses all this and doesn't require Jacobians, so that's a major advantage it'll turn out when we get to that. But in this case, I Jacobian, which was just a derivative, but a somewhat complicated one, and applied it. So, the familiar car tracking example, and I'll cook up some more examples. So this is using just the standard resampling method that we've all used. I haven't changed anything here. This is what you've seen before. You can see where it resamples, and this should look familiar. The particles start to spread apart, and then they collapse. These are the weights. You've seen these slides unusual. And then this shows when they resample. I rewrote this code a little bit to draw a vertical line at the resampling times, and also indicate how many down here, just for the sake of convenience or some of the benefit. And then this was the estimated confidence intervals and all the things we've seen before. It worked really well, even though it's a meager particles. And this is what it looked like, same run, same measurements, same true state, what it looked like using this linearization technique. And when you look at it, it looks a little different. You don't see as many sort of explosions and then collapse. And it's partly because the particles are being guided to be consistent with the measurements that were generated. So it looks a little bit different. At the end of the day, you look at this, still had to resample the instant. It wasn't optimal in that sense. And if we look at the number of effective particles, it still decays, but we only had to resample 14 times instead of 20. And the estimate of the density still looked good. It looked good before, though. And so this is a side-by-side comparison of using the technique we had talked about without this feedback of the measurements, and this is using the measurements to help guide where the particles are located. And the estimates of the densities are basically indistinguishable. They're both good. And then, again, when we look at the number of effective particles, it looks like, okay, so you got 20 here, you needed 14 here. We've got all this stuff. You can make mistakes with a Jacobian. You've got a lot more math you have to do. There's matrices involved. It's more complicated. There's more computation. Although the weights decay, the number of effective particles decays a little bit more slowly, 25% less, fewer resamples, they're still decaying to zero. And so, it calls into question, well, why bother? You went through all this work, and as I told you, this works pretty well. And the vanilla version, it's not a big difference. So the conclusion I drew last time I taught this class is it's not that big a difference. Focus, just use this because it works well. But for this class, I did example, and I made it linear. So this is the model. I made this big, so I'm giving the state a really big kick from one time sample to the next. That causes the particles to disperse and scatter a lot. The knowledge in this case is not so much in the dynamics as it is in the measurements. I made the measurement noise small. So a small measurement noise, there's a lot of value in the measurements, and the state dynamics aren't giving us that much information. And so in this case, I deliberately tweaked this. I chose a huge variance here and a small variance on the measurement, specifically because I wanted to see if does the guiding of the particles really help in a better case. So if you go through and you look at the examples and prior 500 particles, this is the run. They look very similar because the measurement is very similar to the state. And with the resampling, this is what it looks like. The particles, as you expected, sort of scatter at each time step and sample very frequently. So in this case, with the standard resampling, I had to do it 161 times in a run of 200 time steps. Almost every sample, and one of the examples you presented today had something similar where you had to resample almost every time. I think it was yours, Nathan, if I remember right. With this feedback from the state, though, in this case, it resampled once. So in this particular example, there was a huge improvement if what you care about is how rapidly the weights decay, how frequently the particles end up in improbable regions, and wanting to avoid having to resample all the time. Huge improvement in this case. So thinking about using this, results are going to vary. This is just a review of the concepts. I'll skip that and hit this. This is the key slide. What we've been doing is this. I just showed you a way to do something approximately like this. And results will vary. It depends on how much information is gained by including this YN. And I haven't done what Nathan did, where I look at, well, how much more computation did it cost us? And of course, that's going to depend on the specifics as well. So, do you use this approach or not? How much is it really going to help? Does it make more effective use of the particles? Yes, it certainly does. But does it make more effective use enough? Is the gain enough that it's worth spending your computation on the extra linearization and guiding your particles, or should you just throw more particles at it? It depends.
Did you mind posting this code? Is it?
Yeah, I did actually, just before class, so it's up there now. So you'll have it. So, and again, we'll talk about a better way of doing linearization later in the term, but that's the feedback on the importance densities. So we'll stop there today. Thanks, guys. Have a good weekend. And I'll be updating homework 4 so that it's more consistent and encourages you to do a multi-dimensional example for the homework next week.
Which are the slides you're going to go over next week?
Well, I may create some new ones, Jeff, since there's a lot of interest in multi-dimensional, so I'm inclined to just generate some multi-dimensional examples and talk about some of those issues.
Yeah, good.
So it'll probably be a new set, and then after that I'll circle back to auxiliary particle filters.
I won't be here next week. I'll be in physics travel, but I'll for the next slide.
I'll be really careful about saving